It says you're gone. Calvin. It says you have a school activity.
Oh, it's for the rest of you sure?
No. He actually cares about his grade in my class.
Hey, I've been here 2 straight days during my lunch.
That is true.
And I finished the whole unit.
Air 5.
I was yesterday.
I feel math every day. Love math.
Today we do a little bit of English or something.
I'm going to teach you a new calculator function.
Bro, you know this? What if it's that could be like
There's an app top.
problems of one where you can use like simple math for each one. But it's just three completely different numbers. And you just like it's so easy.
But that's what we're doing. We're just plugging in different numbers each time.
You hear what I said though about like old test needs to be like 3, just like this like math problem, but it's different numbers. This is so simple.
I don't know, this is just like...
And this is like you have to like take information and make the problem and
So like
write
2
it.
plus 2 and then 2 plus 4 plus 4.
Hannah.
I'm just saying.
That's literally what you're saying.
Bro, it's just like this.
All right. How many of you read the problem? The sentence, not sentence. Yeah, sentence. Although maybe it should be a question mark. I don't know. It says find the probability that the difference is at least as large as the value the attendant observed. So the word difference tells us we need to do some subtraction. If you go back and reread it, it tells us that a particular type of car has a normal distribution with a mean of 1.4. And a standard deviation of 0.3. The other part, the 1.1 and the 1.9, that's to tell you what to use for your x values on your curve. Because we want to find the probability that the difference is at least as large as what the attendant observed. And the attendant observed one car had 1.1, the other had 1.9. So that's a difference of 0.8, which is why Shelley used 0.8 and negative 0.8 on her normal curve. Difference tells us to find the mean and standard deviation of our normal curve, that we need to find the difference of the cars. So she defined D to be x1 minus x2. x1 is the first car selected, x2 is the second car selected. Both cars have the same mean, 1.4. So when we subtract, we're looking at 0 for the mean of our normal curve. We can't subtract standard deviations. We add the variances and then square root. So you get 0.424. And she labeled all her little standard deviations on the graph. And because it says at least as large as the value the attendant observed, that means the first car minus the second car could have a difference of 0.8. Or the first car minus the second car could have a difference of negative 0.8. Doesn't specify that the first car has to have the higher nitrogen oxide levels. Just says one of them has to have 0.8 or higher. So it's a two-tail one like we did at the end of class yesterday. So she chose this tail when she plugged it into the calculator. Lower bound 0.8, big number, mean 0, standard deviation. And then the symmetry of the curve tells us that this area can be doubled to get our final answer. Questions? Calvin? I'm sorry. Right here? It says 1.4, the mean difference is 1.4 minus 1.4, which is 0, which is why her normal curve is centered at 0. Any other questions? All right, so today we're going to start talking about binomial variables. Specifically, we're going to focus on the binomial setting. We're going to learn a new formula and a new calculator function. All right, so first thing we're going to talk about is the binomial setting. And there is 4 things we have to check for to determine if we're working with a binomial variable. The first one, B, binary. Each observation, I guess I should ask first, binary means what? 2, right? Binary code, they work with zeros and ones. There's only 2 options. So that's what it means here. Each observation falls into one of just 2 categories. Those 2 categories are called success and failure. And I made the B bold, but it doesn't really stand out a huge amount on the paper. Not as much as I would have thought it would. I, independent. The N observations are all independent, which means knowing the outcome of one trial has no effect on the next. Same definition of independent from chapter 5. The probability that A happened had no effect on the probability of B happening. Same definition. And again, I tried to make the I, well, I did make the I bold, but it just doesn't really stand out. Yes, sir?
Yeah, what's wrong with that?
There we go.
Oh.
I have been very upfront about that one. I don't know the difference. And I'm sure that Nate could tell me the difference, and it'd go in and right out.
One's a verb,
Probably like some of what I say to you guys does. So, I get it. All right. Third one, number. There is a fixed number n of trials, or sometimes they'll call them observations. So just keep that in mind. Usually they're called trials, but you know, math, we like to use multiple words for the same thing. And then the last one, success. The probability of success, which we use P for, is the same for each trial. So down below in a minute, we're going to check and see if some situations meet the binomial setting. And so we're going to check bins. Binomial, bins. I got lots of little acronyms for you guys. B, binary, 2 categories, success, failure. I, independent, 1 outcome doesn't affect the next. N, the number is set. So there's a fixed number of trials. And then S, probability of success is the same for each trial. So a binomial distribution is the distribution of the count X of successes in the binomial setting. Sorry, I butchered that. Binomial distribution. And we have certain parameters. N, which is the fixed number of trials or observations, and P, which is the probability of success, which is the other fill in the blanks. I just said it ahead of time. The possible values for X are whole numbers from 0 to n. Because n is the number of trials we have, so that's where X stops. As an abbreviation, we write binomial random variable X as a capital B, N, comma, P. So when we were working in a normal distribution, it was capital N, mean standard deviation. Here, we're going to be working with a binomial distribution, and the 2 important parameters are the number of trials and the probability of success. Now we're going to look at determining if things are in the binomial setting and have a binomial distribution. Can I move it up? All right, so down below, I have 4 of them. I'm going to do the first one, and I'm going to let you guys try some. So the first one says, you observe the sex of the next 20 children born at a local hospital. X is the number of girls among them. So we're going to determine if bins is met. So the first one, B, binary. Do we have 2 categories, success and failure? So we're interested in the number of girls. So that means that female is a success, male is a failure. I'm glad I got some chuckles out of that. I do that on purpose. Love that one. Girls are I can't say the word anymore. That coming from a mom of 2 boys. Got 1 girl though. Yes. All right. And then we're going to move on to I, so independent. So does knowing that the first baby born is a girl have any effect on whether the next baby born is a boy or a girl? No. So they are independent. Then we have N. The number of trials or observations are fixed. What is our N? 20. We're only looking at 20 children. So here N is 20. And then the last one, S, the probability of success is the same for every trial. What is the probability of having a girl? 50% or 0.5. So, and it stays the same every time. So here, this situation is a binomial distribution. So you guys are going to check bins for 2, 3, and 4. Talk with your neighbors if you get stuck. Let me know if you have questions. No, it's okay. Is one of those for people? Can I press some paper in there? Thank you. They used to leave one right there, so I would just pick it outside. Thank you. What?
I want to see how it looks on camera from the dimension.
Oh, if we have time, I'll put it
The
on.
number isn't fixed.
I don't know what to say for tonight.
Wait, Rose. Miss my groups. Oh.
Right. No. So it must be.
Yeah.
If there was, there would be all of them.
Uh-huh. be some other thing, but it threw me, Nate.
I don't know how things like right up to like last week. Like when you were showing me something.
Years of tutoring and
I don't know if that wasn't. Yeah, I thought that was some question.
Zach's going to put the answer to number 2 up for us. Yeah, reread it.
It's the first two, not the last. I did it first one.
Geometric. It's pretty much this, but without it.
No, don't.
Besides the normal curve and the chi-square curve. Chi-square. Gotta figure it out. Skewed right. Thank you, ma'am. Alright, so most of you had no problem on number 2 figuring out that it was not binomial because we didn't have a fixed set of trials. On 3 though, there were quite a few questions about it. It has to do with the fact that you get extra instruction. So if you go back and read, it says that when it's a girl, right? When she gets a question wrong, the computer gives an explanation and additional instruction before moving to the next question, which in theory should change the probability of success because you're getting extra help. So they are not independent because when you get one wrong, you get an explanation that should help you do better the next time. All right, and then Molly is going to do the last one for us.
This beam, and you know what sucks? The pool is like water press is like really hot, right? But the air is so cold. And so when I just smack my face,
Thank you, ma'am.
I remember I did like a fire and it hurt. Really?
We're just gonna chalk it up to nobody cares about effect or affect but Nate. I don't care, effect, affect. The one thing though that I didn't catch before I had Molly come up here, the number of trials is 8. It's a shipment of 10,000 switches, but he's taken an SRS of 8. So the number of trials is 8. Sorry, Molly. Usually I'm better. I missed that one. All right. Any questions? Yes, sir.
How do you feel about Chipotle?
I've never eaten it, so
That's 2.
you both gave me a really weird look. I don't eat fast food.
It's not
bad.
Is it?
It's actually natural.
It's actually good.
It's hella organic.
Is it quick?
It's yummy.
That's fast food.
Yo, Chipotle after workouts.
Chipotle's not even that much.
Don't even look at you, Tyler. You just
I am
The burritos though?
never
No, you get a bowl.
Never eaten it in and out. Never McDonald's. When I was little, we used to go to Burger King every once in a while.
Burger King was good. The stuff is cold. The Whoppers, just as big for
Eat fast food. All right. Now, boys, we're gonna look at some more math. So in a binomial setting, we can define a random variable, say x, as the number of successes in n trials. And then we can find the probability distribution for x. So our example here is this paragraph in the middle. So each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable with n equaling 5 trials and probability P equaling 0.25 of a success on each trial. In this setting, a child with type O blood is a success, which they use S for, and a child with another blood type is a failure, which we use the letter F. So what's the probability that X equals 2? So what's the probability 2 of the 5 children have type O blood? Well, what's the probability? Well, I'm going to backtrack. Before we do that, it does say that it is a binomial random variable, but let's double check. So B, binary, we're told type O is a success and another type is a failure. So the B part is met. Then we had I, independent. And a lot of times with these type of problems, it'll be given in the problem. And I think I said that last time too. But there will be some sort of sentence that just says we can assume independence. So I underline the sentence that tells us it's independent. And so what you'll see me do is I'll put quotations around the word independent, or in this case, the word they say is independently. And by putting quotations, I'm just saying it's given in the problem without actually having to use all those words because I'm lazy. N tells us that the number of trials are fixed, and they gave that to us in the paragraph. And they also gave us P, the probability of success is 0.25. So, we want to find the probability that x equals 2. So 2 of the 5 children are successes. So another way to think about that is the probability we have is success, success, failure, failure, failure. So what's the probability the first kid's a success? I think I heard somebody say it. What?
20%.
25%. So what's the probability kid number 2 is a success? What's the probability kid number 3 is a failure? And the next kid's a failure? And the last kid, failure? 75%. So I could simplify that and say 0.25 squared times 0.75 cubed, right? That's really what I'm doing. Taking the probability of success, raising it to the number of successes I want. Probability of failure raised to the number of failures I want. And so we have 0.25 squared, 0.75 cubed, and then we're going to multiply those together. So that answer times that one. And we get 0.0264 when I round. Make a little squiggly, 0.0264. Any questions on that? Anybody take issue with that? Yeah, I did something wrong. Well, not wrong, but I assumed something that isn't necessarily true. Nobody? So, I assumed the first 2 kids have typo blood. Order matters. The first kid could have not typo blood, and the second kid could have typo, and the third could have typo, and then the last 2 don't have typo. So I assumed that the first 2 were successes and the last 3 were failures, but there are a bunch of different combinations of having 2 successes and 3 failures in 5 kids. So we're going to come up with the list of all the different ways. We can have 2 kids with typo blood and 3 without. We're going to use S for success, so they have typo blood. F for failure, they don't. I already gave us one. The first 2 have typo and the last 3 do not. I try to be methodical when I make these lists. So I'm going to leave the first S there, and I'm going to move the other one. So it could be a success, then a failure, then a success, then 2 failures. Or it could be success, fail, fail, success, fail. Or I could have success, then 3 failures, then success. So that took care of having the first one being a success. So now I'm going to say, okay, if I have a failure first, then 2 successes, then 2 failures, I'm going to leave the first S alone. So fail, success, fail, success, fail. Fail, success, fail, fail, success. And that takes care of having S in the second place. So now I'm going to move to it being in the third and fourth. So fail, fail, success, success, fail. Or fail, fail, success, fail, success. Right? Yeah, and then fail, 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 success, success. And I think I covered them all. And that, remember, is our sample space for having 2 successes and 3 failures out of 5 kids. So there are 10 different ways, right? If I counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different ways that we could have 2 successes and 3 failures. So really the probability that x equals 2 is going to be 10. The 10 different ways I can have 2 successes and 3 failures times the probability of success raised to the number of successes I want times the probability of failure raised to the number of failures I want. So really we're just going to take the answer we got before and multiply it by 10. So the probability that these parents have 2 kids with typho blood out of their 5 kids is about 26.5%. Questions? No? All right. I keep assuming I'm going to get these. You guys notice I had a certain order. Now I was assuming that somebody was going to say, really, we have to make sample spaces all the time? No. I'm going to teach you the calculator function. So, we had any one arrangement of 2 successes and 3 failures. They all had the same probability, because no matter what arrangement we work with, we did 0.25 twice and 0.75 3 times. So we can generalize this for any setting where we are interested in k successes and n trials. When you want to find the number of ways to choosing k objects among n total objects when order doesn't matter, you're going to use a combinatoric. Combinatoric calculator function tells you all the different combinations so that you don't have to sit and make a list like we did. Our combinatoric is going to be what we call the binomial coefficient. So 10, that was all the different ways we could have 2 successes and 3 failures. That was our binomial coefficient. Now, your book uses the letter K, if I remember correctly, because I haven't used this calculator function in a year. I'm pretty sure the calculator uses R, at least the newer ones. So just keep that in mind. The book uses K. On the calculator, it says R. So, there are two ways that the combinatoric notation is written. The first, you have a capital C, combinatoric combinations. You have a subscript in front of the C, N, that's the number of trials, and then K as a subscript after, that's the number of successes you're interested in. The other way it can be written is in parentheses with N above K. So the number of trials, the number of successes you're interested in. I'm going to show you the formula. You don't have to memorize it. I just know sometimes kids are actually interested in how it's done. So the formula is I was going to yell and then I didn't.
That would have been fun.
It would have been funny.
You should.
Sure.
It's not too late.
You should. Yeah.
N
Yeah, there you go.
divided by K. No, I just can't. It's so weird. All right. Anybody know what the exclamation means? Or its name? Nate? It's called a factorial in math. And what does a factorial tell us?
It's the number times all of the preceding numbers to 0.
Thank you, sir. So when you have an exclamation in math, that is a factorial. And just like Nate said, it means you take all the previous numbers except for 0. Because if you multiply by 0, you get 0. And you multiply them together. So 3 factorial is 3 times 2 times 1, or 6. Now, like I said, you don't have to memorize this, but this is how they find all the different combinations. The other thing I said, the calculator uses R. And I'll show you where to find it in the calculator in a minute. But in the calculator, it'll have the capital C, the lowercase n, and then instead of K, they use R. I personally like this notation, so that's how you'll see me write it. But I'm pretty sure the book writes it that way. Both of them are fine. All right, so just for the sake of using the combinatoric in the calculator for the first time, we're going to work with the previous example. N was the number of trials, so we were looking at a couple who had 5 kids. And then R, or K, is the number of successes you want. So that would be 2. So this was kids, and this was successes. So I made the list, and I found there were 10 different ways to have 2 successes among 5 kids. So we're going to make sure I was actually right. Everybody okay if I cover up what I wrote with my calculator? All right, you're going to go into math. Yay. And you're going to go over to prob, and it's number 3. And right below number 3 is the exclamation mark, the factorial. You want NCR, not NPR. NCR, so number 3. I'm going to show it on the newer calculator first. The older calculator has to be typed in slightly different. So if you're working with a newer calculator, you can go in and choose this, and it opens up little subscripts for you. So I had 5 kids, oops, and I wanted 2 successes, and then I hit enter, and I get 10. which is what I got when I made the list.
It just says NCR for the old one.
Right. So on older calculators, like Zach was saying, if you go in and you choose the NCR, it'll take the previous answer. You have to type the number of trials in before you go in and do that function. So you have to type 5, then go into math and choose NCR. And then we want 2 successes. And then you hit enter and we get 10.
Wait, why do you have to hit 5 before?
Because it's the way the older calculators work. It's just,
It's so weird.
back when they made them, programming wasn't as advanced. I don't know why you have to type it in first. The calculator I used in high school, you had to use backwards Polish notation.
What?
What?
Backwards Polish notation.
Yeah.
What?
You had to type things in backwards. I don't know the whole Polish part. Maybe because the calculator was originally made in Poland or something. I don't know. It was an HP 48G. It was amazing. It would do calculus for you. No, it was handheld. It was really spendy though. So they only had a few for calculus students to check out from the library. And then I also had my TI-83. But the HP 48G would, like, you could type in a calculus problem and it would do it for you. What?
How many calculators have you gone through the years?
Well, I tried to take good track of them, good care of them. So I have like 10 or 11 personal ones right now that I loan out when kids forget them. In high school, I had one and I put it on the ground. I wasn't in math class, I was in German class. And then we had to move our desks and it fell off. And my friend put the corner of the desk. She didn't do it on purpose, but it was right on the screen and then sat down. And it's,
I feel like she did that. It was racially motivated.
yes, because she was white and I'm white. So,
It's racial evidence.
yeah. All right, back to math. You guys are really trying to get me off topic here. Do not get intimidated by this. I have already taught you this.
Like volleys or what?
That formula, that's the formula on the AP formula sheet. But I already taught you all of that. I just didn't put it into letters. Okay? So we found the probability that we had x equals 2 successes. I showed you on the calculator how to do the combinatorics. So 5, choose 2 successes. We did the probability of success, 0.25, raised to the number of successes, 2. Probability of failure, 1 minus 0.25 or 0.75, raised to the number of failures, or n minus the number of successes. So we already did this formula. It just looks really intimidating when you put all the letters in there.
You don't have to know that, right? Like for your tests?
So yes.
It wouldn't hurt. I mean, it's really not a difficult thing. Probability that x equals 2. You have to know the number of trials, number of successes, which I showed you how to do in the calculator. That gave us 10. And then we took our probability of success, raised to the number of successes we want, times the probability of failure, raised to the number of failures we wanted. It really isn't a hard formula. It just looks ridiculous when you look at it with all the letters.
Yeah, I don't like letters in math at all.
Yeah.
Why did we have letters in that?
Facts.
We just decided to put letters in that.
Who invents math?
Who did that? Who made this?
The Greeks.
What?
Anywho, now we're going to practice using it. So that whole box was just to show you. That is what shows up on the AP formula sheet. It looks a lot more scary than it is.
So we have to memorize this.
Okay, is the
But it's not that hard to memorize. Number of combinations, probability of success raised to the number of successes, probability of failure raised to the number of failures. Hannah?
what is the 5 and 2? Like, is it?
That's the other way you can write combinatorics. It's the same thing you just did in the calculator. There's two notations for it. And if I put a C in there, you guys really get mad after the N's, the K's, and the P's. And I threw a C in there, you'd be like, what?
Just go to the alphabet.
Did you show on the old calculator yet?
Yeah.
Yeah.
So for the old calculator, you have to type in your number of trials first. So you have to type in 5 first. Then you go into math, go over to prob or PRB in the older ones, and it's number 3, NCR. And then we have 5 trials and we want 2 successes. And you hit enter and we get, there's 10 different ways we can have 2 successes and 5 trials. Any other questions? So like I said, we're going to practice using this part now. So we have example 1. We're going to roll a die 5 times. X represents the number of 4s that appear. So N, how many trials are we working with here? 5, because we're going to roll the die 5 times. P, so probability of success. If X is the number of 4s, a success is rolling a 4, and a failure would be rolling anything other than a 4. So what's the probability of success? 1 out of 6. Thank you. I guess I should put that off to the side. Fail would be 1, 2, 3, 5, 6. So the probability of failure, success is 1 out of 6. So if I asked you to find the probability that X equals 1, we get 1/4 out of 5 rolls. We would do our combinatoric. So 5 trials, we want 1 success. Then I'm going to multiply that by the probability of success raised to the number of successes, which is 1. And then I'm going to multiply it by the probability of failure. So success is 1/6. So probability of failure is 5/6, because there's 5 numbers that are failures. And we have 5 trials, and I only want 1 of them to be a success, so that means I want 4 failures. So we're going to go in. I'm going to use newer calculators, sorry people. We're going to do our combinatoric. By the way, I don't think everybody knows this, but I already did a combinatoric. So I can hit second enter and it'll just re-enter what I had put in there. And then I can go with the back arrow and just change 2 to 1. So I don't have to go through the whole math and all that. I mean, that's really not that hard, but that was like 2 buttons I pressed. So there are 5 combinations of rolling a die 5 times and getting a 4 once. Then I'm going to take that and multiply by 1/6 to the first and 5/6 to the fourth. So I have 5 times 1/6 to the first, which means I don't actually have to put the exponent, times 5/6 to the fourth. And we get 0.402 when I round. Do you have a question, Eric? No? He's on his phone. All right. So then what's the probability that we get 2 4s out of those 5 rolls? So we would have 5 choose 2. Probability of success raised to the number of successes. Probability of failure raised to the number of failures. We know from the previous example the 5 choose 2 is 10. So I'm going to do 10 times 1 6 squared times 5 6 cubed. And I get 0.161 when I round. No? Yes? No?
I agree.
It looks like a really scary formula, but to me it's actually one of the easier ones to use. To me, yes. Tummy. Okay. Let's see. We have about 9 minutes left. Go ahead and try number 2 really quick. Identify N and P. Find the probability that you make 1 free throw or you make 2. Probability of success. You're right. Yeah. How many shots were taken?
I'm sorry.
I am very sober right now. What are you talking about? I get to the day.
What's the probability?
Wait, I got a question. That is not
Maybe
my
I want
fact.
to.
I'm sorry.
That's not a fact.
No.
So how do you multiply? So how do you correct it? Oh, that's the.
The combinations. The NCR.
You're reaching up there, Michael.
So you have 5 for your trial. So type 5.
Then go to math.
From
So,
here.
I do
3.
5
And then
numbers.
1. I don't even know where to
Oh, 1.
Oh, okay.
No, I'm talking about how do I do the whole thing? So how do I take the whole thing out?
Probability.
Well, I do that separate.
Okay.
And then you
So
would
that would
do
be
5 times 1
to the
6.
power of 1.
And I use parentheses to multiply. You just have to check the 5.
Okay. That's probably
Parentheses, 1 6. So 1 divided by 6.
greatest to the
Close parentheses. Now it's raised to the first power, so I can check.
This page
And
is
then open another
Five
parentheses, 5 divided by 6. Close it. Raised to the fourth. If the probability of success is 80%, the probability of failure or missing is, yeah, so 3.2.
No, I didn't. I can't fully erase this
And
page.
the 0.2. Yeah.
Wait, what did I do?
Now,
That's
you want to go put them on the board for me? Actually, you know what? I'm just going to write them up. All right. Sorry, Anna. I want to look at the next page before we leave. So, all right. We're taking 5 shots. The person's an 80% free throw shooter. So we have 5 choose 1, 0.8 to the first times 0.2 to the fourth, which comes out to 0.0064. Yes. And then we have 5 choose 2, 0.8 squared and 0.2 to the third, which comes out to 0.0512. Not as many yeses on that one. If you are struggling to type it into a calculator, let me know in a minute and I'll come around and help you, okay? Down here, it was just having you guys derive the formula, but we're going to skip that for now. We're going to go back to the blood type example really quick. So each child of a particular pair of parents has probability 0.25 of having blood type O. The parents have 5 kids. Find the probability that exactly 3 of the children have type O blood. Let X be the number of children with type O blood. We know that X is a binomial distribution and is 5. P is 0.25. So this time we're finding the probability X equals 3. We still have 5 trials. We want 3 successes. Probability of success, 0.25 raised to the third power. And probability of failure, 0.75 raised to the 2, because we want 2 failures. Sam. Okay. So I need to figure out 5. Oops, I hit the wrong one. 5 choose 3 is 10. And then I have 0.25 to the third times 0.75 squared. Ooh, no. Sorry. I left it all in the exponent position. Squared. And then I want that multiplied by 10. So we get 0.088 when I round. Part B says, should the parents be surprised if more than 3 of their children have type O blood? So to answer this, we need to find the probability that X is greater than 3. Since we have a fixed number of trials, X being greater than 3 is X is 4 and X is 5. So we're going to find the probability that X is 4 and add it to the probability that X is 5. So we're going to do this part over here, because I can't write that small to make it fit under there. So 5 choose 4, and I'm a goofball. It is not a fraction. Don't know why I put a fraction line. That's not going to write on there anymore now. 5 choose 4, and then we have 0.25. We want 4 successes times failure. There's only 1 failure. And that's going to come out to some number for us. And then probability that X equals 5. we're going to do 5, choose 5, which, by the way, 5, choose 5 is just 1, because there's only one way you can have 5 successes and 5 kids. And then we have 0.25 to the 5th, 0.75 to the 0, which, remember, anything to the 0 power is 1. So really, this is 1, that's 1, so the probability x equals 5 is just that middle part. So 0.25 to the 5th. And remember, if you get e with a negative number after it, it's got a bunch of zeros in front. So this is about 0.0009. And then we have to do 5, choose 4, which, if I remember correctly, is 5, yeah. 0.25 to the 4th times 0.75 times 5. And then we would add those together. And there's about 1.5% chance they have more than 3 kids with type O bloods, so they should be surprised. Thank you.
I'm